Given the matrix M, and we're asked to use it to transform the unit square. So B is 1, 1, A is 1, 0, C is 0, 1, of course the origin is 0, 0. And we're asked to then sketch what we get out of it. So what we can do is actually take the fifth out. That's a good idea, just to make calculations a little bit easier by hand. So it's a fifth times minus 3, 4, 4, 3. And then to multiply it by the unit square, you can either just times by the coordinates in turn, or you can write it as a nice 4 by 2 array. We've got 0, 0 for the origin. Then A is going to be 1, 0. B is 0, 1. Sorry, because it's, sorry, C is 0, 1. And B is actually 1, 1. So basically I can just transform it all in one go. We're going to get 0, 0 for the origin. But then for A, it'll be minus 3 plus 4, so minus 3 for that one. I'll keep going along actually, then minus 3 times 0 plus 4, I'm going to get a 4 here. And then minus 3 plus 4 gives me 1 here. I've just been using this row and each of the columns to create them. And then here I've got 4, because it's 4, 3, and 1, 0. Then I'm going to get a 3 here. And then 4 plus 3, 7. So that will become 0, 0 for my, where the origin's gone, it's not gone anywhere. Then minus 3 fifths and 4 fifths. That is going to be my coordinate A dash. 4 fifths and 3 fifths for C dash. 1 fifth and 7 fifths for B dash. I can write on those coordinates. I think I'll draw them on the graph and then label them as their coordinates. Okay, so of course we've got, yeah, this one the same. We're just doing this roughly to scale. It doesn't have to be perfect. So I'll go with minus 3 fifths, 4 fifths. Okay, so that's going to be about 1. So maybe it'll be, I might just split it up into little sections. 1, 2, 3. So that's 5. Okay, that's not too bad. All right, minus 3 fifths, so that's minus 0.6 and 0.8. It's going to be here. That is my A dash. Then 4 fifths and 3 fifths. One fifth, or 0.2 and 1.4. Actually, we're going to be going up here. Oh, sorry, I went a bit too far. Actually, 1.2 is going to be here. No, wait, it is 1.4. Sorry, I should have gone another one. And finally, I'm just going to join this up. Now, one thing to say is that this is not a rotation. It looks a little bit like a rotation when you look at the square, but A has actually gone over here. So it's not like we've just rotated it around like this. See, because B seems to have rotated to here, but then A swapped around. It's actually a combination of transformations, a reflection in the y-axis and then a rotation. because you could write it, and I was playing around with it earlier actually, you could write it as, I think it was -1, 0, 0, 1, and that is a reflection in the y-axis multiplied by something that becomes a rotation. We get 3/5 and then -4/5, 4/5, and 3/5. Because then you got these two both being positive, these having different signs. That's kind of your code for a rotation. I'm not going to go into more detail on that. It's not actually relevant to the problem. It's just like, it's not quite a rotation, but it's, we'll see later on when we talk about the determinant, like how it all comes into play. So part 2, we're asked to find the equation of the line of invariant points of this transformation. So I'm going to start by finding any invariant points. I think it's just going to happen to be a line. Now for this, we can again take the 5th out, and I think that's a good idea. Okay, you don't have to. So I'm going to multiply the matrix now by a point. We can see that 0, the origin, is an invariant point, but are there any more? So our general coordinate would be xy, which we write as this column vector. And for it to be invariant, it doesn't go anywhere. So then it's going to equal xy. That means that a 5th times -3x plus 4y, and then 4x plus 3y is going to equal xy. And that means that -3x plus 4y is going to equal 5x. I've just multiplied through by 5, and then I'm just writing the top row out. And 4x plus 3y is equal to 5y. Let's deal with the top one. We're going to get 8x equals 4y, therefore y equals 2x. And the bottom one, we just need to check if this brings anything else into play. 2y equals 4x. So again, y equals 2x. Both of them give this. This is going to be the line of invariant points. Sometimes you can just get a single coordinate, but we actually have this infinite line. Y equals 2x, so actually it would be, I mean, we don't have to draw it on, but it would be anything sort of along this line here. It's not obvious to see even by talking about a reflection and then a rotation, but we've shown it algebraically. Find the determinant of them. So remember, if you've got A, B, C, D, then the determinant is AD minus BC. So for us, it's going to be, I'm going to leave the 5th in this time. It's going to be -9/25 when I do -3/5 times 3/5, then -4/5 times 4/5. This gives an answer of -25/25 or -1. And then finally, we're asked to briefly describe how this value relates to the transformation represented by M. And there's two aspects actually. There's a couple of marks here. We need to talk about what the 1 means. The number itself, like ignore the negatives, gives you the scale factor for the area. So in this case, the area stays the same. However, the negative, that doesn't mean you get a negative area or anything. The negative is to do with the orientation, a little bit like with enlargements when you have a negative scale factor. You might start off with a triangle looking like this and it ends up upside down. That's what the negative means. The orientation changes. And that's kind of where this bit comes in. So the rotation actually doesn't change the orientation. It's still kind of, I know we've tilted it, but that would give you actually the determinant would be 1 for any rotation. But it's this bit here where the -1 comes in when we do our reflection in the y-axis. Again, you don't need to go into detail, but you do need to say the orientation will change. And I talked about it at the beginning, like the A's kind of gone over here, but the B is like seems to have just turned a little bit. That's because of the combination of transformations. Okay, nice question. Well done.